I want to.
This is not reaching.
Okay, so how do I get out of here?
I'm going to mute myself.
What, extension cord or more plug strips?
I just need to go.
Quality psychiatric care?
Oh, definitely quality psychiatric.
Can't figure out how to get out of this thing. Exit.
Oh. We have audio.
You have audio. Okay.
Now the question is, if I push this button, okay, so that I did. So what I want is default microphone. So testing 1 2, testing 1 2, testing 1 2. No, I'm still getting audio.
Okay.
Testing.
Okay. Okay.
Oh,
Listen.
we have
Hello.
Testing 1 2.
Okay.
There we go.
Got it?
We have audio.
All right.
We're good to go.
Okay.
When you
Good.
plug it in the right port. It works better that way. Yeah. Yes.
Wow. What do I have here? Gee. Yeah, I know that. Oh, this is Korean. Okay. Yeah. This is very popular in Taiwan too.
Yes.
It's a bit sour.
Huh?
A little bit sour.
A little bit sour, but it's got the active culture.
Yes.
Stay alive. Thank you.
Okay, you're welcome. Okay.
Streaming or streaming? I'm still getting up the other camera, but.
I will get that. Okay.
Ting, welcome your viewers and on the show, I guess.
Oh, well, I think we can wait for you and the new guest.
We're waiting also for some.
Uh-oh. They're coming for us.
Okay, I'm ready. Morning. A cup of tea? All right.
Oh, no, that's the Google Plus U event hangout URL. And I just lost my window. How did that happen? Oh, there we go. Oh, there's a fancy little link thing down there now. On the one hand, it's easier now because you can actually start a Hangout from YouTube. Click the upload button, click Hangout, and it's wonderful. And it works.
So we're running now?
We're actually streaming now, including my big ugly mug.
So we're all here. Thank you, everybody.
Okay. All right. Good morning, everybody. Welcome to the Silicon Valley Northeast Group, and we are broadcasting from Stanford campus. Okay. 如果你会说中文的话，欢迎你到这个西武的无耻协会。我是丁陈汉生 ，I'm Tim for short, Chen Hansen Tim for long, and welcome. Today, this morning, I'm going to talk about the discovery, irreducible complexity, E4 for discovery. And discovery, if you can remember, a couple years ago, the ST Microelectronics, they put out this STM8S discovery. We sell it for about $8.50, and it was a very nice kit. But it's an 8-bit microcontroller. But that 8-bit microcontroller is almost a 16-bit microcontroller. So it has lots of things that a 16-bit micro would do, and it did it quite nicely. But I put a fold on it. Nobody seemed to know this. Yeah, since I don't get any orders on my website. So that's it. And recently, they have released this new discovery. And that's STM32F4. That's a 32-bit microcontroller. The kit, the first time I ordered it, it's $14.90. But next time I ordered, it was $20 something. So, but for $20, it's still a steal. Very nice, very nicely done kit. I wasn't paying much attention to it because I thought, well, I have retired. I don't have to worry about any of the new things. But then the people in Taiwan SVFIG, they were developing this board called 4Uno. And this is it's using the same microcontrollers here, but if you look at the board, it has lots of optically isolated input and switching transistor driven output. So, you know, it's very apparent that they intend this board to be used in real industrial applications. But it's using the same chip as we have on this board. So I thought, well, you know, probably I should look it up just to see what it is. And looking through the documentation of this board and this chip, I was kind of amazed at how many things they have crammed into this little chip. So today I'm going to talk about the board that I put on. And here are 3 experiments that I'll show you. So let me tell you about these experiments. So in the middle, it's this board, okay, and it's this board itself. The chip has 6 USAR ports. So there are lots of communication capabilities in it. But I only need 1. So I picked USAR 1. But this board does not have a direct connection to the USB port to the CPU. The USB port is used for ST-Link. Okay, so this part of the ST-Link, it actually controls the microcontroller there. So you can download and you can debug and you can real-time monitoring what's going on this chip. It's very powerful. And the interesting thing is that this ST-Link also has a JTAG and port. Okay, so if you are not driving this chip on the board, you can pull out these 2 plugs and then talk to another chip through this port. So this is what I'm doing here. This board now it's not connected to the chip, but it's connected to this 4-Arduino board. And I'm just last night I was able to get the connection going, and now I'm very pleased. So this way, because this board, it has the UR port is connected to the PC through the USB, so you can actually talk to the host through the USB port. But it doesn't have that USB port. Is only a serial communication port, and there's no debugging facility. So I was very happy to find out they have pulled out these 4 of these pins into this connector, and I can connect them here. So this pretty much completes this development cycle that I can get the microvision IDE on PC, and this IDE can control either the discovery board or for Arduino board. Okay, let me just go to the slideshow. And so here, this morning, I'm going to talk a little bit about ARM7 E4. the little bit of history of it. And then mainly on this STM32E4, currently it's version 7.20. And the title is Irreducible Complexity, so I talk about that. And then this kit and this chip on board really allows you for non-constrained experience. Lots of capability within this chip, within this board. And I'm going to do a little demo of these two boards. So that's what I'm going to talk about. Okay, I have worked on the ARM7 chips for more than 10 years. It was when it started. It was in 2000 when I was in Taiwan, and there a very young engineer Wu Jianjia, and he's porting eForce over to an ARM7 development system. So that was very impressive. Just one day he came in with a board. That board is also very nice. It has a 8-inch LED on it. So he is showing here. Push the button and it says OK. Wow. So that was the start. And then in Taiwan in the year 2000. The Game Boy Advance was very popular. Okay. Game Boy Advance, if you have anybody has this Game Boy Advance. Okay. This has an ARM7 chip in it. I think I'll talk a little bit about it. So we ported the eForce over to the Game Boy Advance, and really this is it's for a game, but it's using a flash cartridge. So Nintendo at the time they released complete documentation on this device, so that people and they even have programming manuals and all the details. So game developers can use it to write games. So we use it for lots of projects. I think I show some of it here. And then that's a version 2. We ported over to the Game Boy Advance and improved it a little bit. At the time, the eForce, I was improving on eForce mainly on the 8086 eForce. And so we went to 8086 and go to the 186, 286, and 386. And that is, so the version 0.2 gets into version 0.3 and get into version 0.4, which was the 32-bit 386 eForce. Okay, so that's a version change to version 4. And then when I in 2004 I start working on the analog device ADUC 7024, and that the eForce at the time I said, well, I just continue on, and it's version 5. And a couple of years later, yeah, so let me show you this this ADUC, analog device. They put up this development system. Very nice system. And so I got a whole bunch of them, and I actually made some force stamps, if you guys remember, force stamp. Okay, okay, let me show. This is the force stamp. Okay, So it has a whole bunch of them. And this is interesting in that it is a single chip computer. It basically has the RAM, ROM, and all the I/Os. So you really don't need any other components. I think you don't even need a clock. But the clock is optional. So that one's nice. Try to sell this for stamps, but didn't sell many of them. So and then Dave Jaffe gave me this board. It has another ARM7 chip on it. So, and the eForce become version 6. Now I'm working on this STM32F407 chip, and naturally it's version 7. Okay, so I think I've talked a little bit about the Game Boy Advance, and we've basically the port we moved out, ported over was the original eForce model, and that's direct threaded eForce model. It's using a Win32 port to do metacompiling, and we have a bunch of applications for that. So that's the Game Boy. Okay. So the Game Boy, it's basically what I want to show you is Game Boy. At the 2000, it has 32 kilobytes of internal RAM. No ROM, no flash, and Game Boy on the kit, Nintendo put in 256 kilobytes of external RAM and 32 megabytes of flash. So that's a lot. Okay, but these are all outside of the chip. That's the technology in 2000. I think Okay, so this is the force stamp, and the ADUC 7024. It's really a nice chip, and it has 64 kilobytes of flash. Okay, and let me see how much. I think it is. Let's say the 64 kilobytes of flash and RAM. I think they can kind of mirror, but I forgot. I think it is 64K flash and 8K of RAM. So that's in the year 2004. So I was able to build an audio scope. You see here. That's the force stamp, and it needs a display. So I'm using the Game Boy as the display. So the chip, the ADUC, has A to D on it, but I think it is the top limit is about 1 megahertz. So with 1 megahertz, there's no problem with audio signals. Okay, so 2008, I was using the Atmel AT91 SAM 7X256. So this guy has 64 kilobytes of RAM and 256 kilobytes of flash. So that's quite a lot. And it has an 8 megahertz A to D. All the stuff, all the goodies. So this is a picture of that, and it has a nice color LCD on it. Okay, now to the STM32F407. So this 407 on the discovery board. The discovery board has the ST link, and that's very nice. Let me see. Okay, the ST link is just top portion of the board, and it talks to USB, and it uses what they call the single wire debugger. Okay, so it is one data line to control, to debug the chip. So this is a very nice setup. On some other earlier systems, they were able to put the serial port, combine the serial port and the debugging into a single USB cable. But this guy didn't have it. I missed that. But as far as the debugger is concerned, it's very nice. So on this discovery board, it has an accelerometer. And I was thinking, oh, how are you going to measure acceleration? But it's not measuring acceleration; it's measuring gravity. Okay. And if you normally if you put the chip this way, it would consider its null position. And if you flip it over, it reads twice the G-force. So that way you can calibrate this chip. So this is very nice chip. And in the demo, they actually have the demo that if you hook it up, power it up, the LED would light. If you push this button, hold it down for 3 seconds, then it turns into the accelerometer mode. And there, if you tell the board, the 4 LEDs would light up according to which direction is on the top. Okay. But I wasn't able to get. I think the first time I got this board, it worked, and then it never worked again. So I thought, well, after a while, I thought maybe I have destroyed it because I was messing around. So I bought 2 more fresh boards, and they didn't work either. Okay, I don't know why, but as far as the demo is concerned, it is very nice. And then it has another micro USB port. This port, they implement a mouse. So if you connect this micro USB port to another USB port, then you get a mouse. And if you tilt this thing, and the mouse will actually move. So that was a demo. But I never could get the mouse to move. But on YouTube, if you look at on the YouTube, people have done all this demo, and must have worked. But it didn't work for me. And it has a very good audio ADC and the DAC, and the ADC runs to 2.4 megahertz. So that's very nice. And it has 3 LCD, 24 channels. Wow. And this one has 2 100-pin connectors. So they bring out 80 GPIO pins. So if you want to use it to do some experiment, this is plenty of resources for you to spend your time. So here you see these 100 pins with lots of I/O capability. Okay, then I think I wasn't really interested in doing anything until Taiwan FIG people sent me the Fortuner board. It used the same chip, but the configuration is different. So when I got the board, I was, oh, how am I going to program it? And I found that it has the UART. UART1 is implemented on the USB, and it is implemented as a COM port. So this is very nice because the chip, when you power it up, you can set the input pin for it to be in the download mode. And in the download mode, it's using the it's looking at all the serial port on board and waiting for a turn on signal. If it receives that signal from any of the port, then it will latch onto that port and do the downloading from that port. So it is very nice. And I told them I couldn't use it. How am I going to turn anything on? So they finally sent me a set of pictures. So do this, do that, do this, do that, and you can actually download the text file into here. So I followed it step by step and got their demo onto it. Then what? Okay, couldn't do any programming. So I was then I thought, well, I will just go to get the discovery board, and with the whole set of tools, maybe I can move forth onto it and do something. So it has on this board it has 12 switching transistors. So I think it, with an external power supply, you can drive lots of circuits. And it has 13 optical isolated input if you want to monitor your machine. The motors, the decoder, encoder, decoder, and all this thing. And the most interesting thing is that why they call it Fortuner. It has all the Arduino I/O ports on board. And not only that, it has all the launchpad I/O pad. I guess that what they intend to do is to use this board to suck in all the Arduino and the launchpad applications. I think that's the intention, but how successfully they are, I don't know. Okay, so this is the Fortuner board. As you can see, these connectors are pretty ready to go into a laser milling machine. That's what they I saw some pictures that they will use this one for a laser milling machine. Okay, so STM32F407. This 407, it is the family is STM32F4. Okay, and the family generally 32-bit Cortex M4 chip, 1 megabyte flash. Different models have different number of flash. Some of them are 550, and some of them has 2 megabytes of flash. So RAM, it has 192. Wow, that's a lot. And you can push the clock to 168 megahertz if you care. And then GPIO, timers, UART, ADC, DAC, SPI, I2C, I2S, CAN, USB, you name it. It has them all. Let me see. So after I got the discovery and start working on it, so I plan to do the target is really two versions, 720 and 730. But to get to the 720, I need to make two versions first. So version 7.01, that's a fourth, which is in Flash, and then execute from Flash. So that's the easiest way. You write the assembly code, download, and it's in the Flash. And if you you boot it, you start it, it will start at 8000000. Okay, at the start of the Flash memory. So that's when the debugger would start it. So I put it there, and then basically single step through the whole thing and get it to work. So that's the easiest one. Then I'll move this. The chip has a very nice virtual memory system. The page zero from 0 to 1 megabyte, that range, that's a virtual memory. There's no physical memory in that space, but with some I/O pins and also the software control, this page can be vectored or mapped to the ROM memory, to the RAM memory, and to the system memory, where you can boot. Okay. So it is in software you can just switch the page 0 so that it points to different areas. But you can execute then the same code you can put in ROM, put in RAM, and you can execute them in page 0 identically. So that's a very nice mechanism. So version 7.10, that's fourth is still in Flash, but it's remapped to page 0. So all the logic addresses are in page 0. So I have to change all these physical addresses from the RAM memory address to the page 0 memory. So that's one step. The final step is to put forth in Flash and copy the entire forth into RAM. And the RAM is remapped to page 0, and then execute forth from page 0. So that's the goal. And this is the because we have enough RAM, so we can run forth in RAM and then extend the dictionary as well. Of course, after you debug an application in RAM, the whole image can be saved back into Flash, so that it can be a key system. So this is the goal. And then for the Taiwanese, as a thank you gift back to them, I put in V730. And this one is mainly there's the board, the Discovery board, and the Fortuner board. They are very similar, but the I/O are different. Okay, so you need code has to be changed to run in the Discovery from in the Fortuner. It's a small change. There's some UART need to be switched around, and that's almost all things that need to be changed. But it's a significant change anyway. Okay, the title "Irreducible Complexity" really refers to the software tools that's provided with the Discovery. So I was getting really confused. Okay, and when you get the ST Microelectronics, they released the complete source code for the demo, and many other demos. This demo mainly is to show the accelerometer capability and also the USB mouse. Okay. So the application it's it's not a trivial demo, and then they have demos for audio capability that you can. It has on board. It has a speaker, and it hooked to the A to D, so you can actually digitize a speech for how many seconds I don't know, and then you can play the speech back. So that was a very nice demo. But all these things are huge package, and the accelerometer demo, I loaded up, got 7 folders, got 31 files, and I said, wow, how am I going to get through all these things? I just want to get my thoughts up. And so I spent lots of time looking for tutorials. Google it and do a very extensive search. I say exhaustive search on the demos for this board. And I think this is the best demo I found was a demo which just increment R1, R0 register. And that was it just almost just have this many lines of code. So it starts up and then do the increment the R0. Oh well, I see. Wow, that's the one I really. That's the entry point I found. Because in all the examples, the first block they put on your path is this startup file, and the startup file is an assembly file, and that's the only assembly file in the system. Everything else are written in C. But looking at this startup file, pages and pages and pages, basically they are trying to set up the complication is to set up the interrupt vector table. And this guy, it has, I think, logically it has 256 I/O devices. And I think physically they implement about 20 or 30 of them. So all this interrupt vector has to be set up. And then there are devices which has to be initialized, some crucial ones. But the program is so long that I couldn't figure out which devices has to be initialized. And finally, this example shows, well, you don't need any obvious thing. All you need is this 2 lines of code, okay? And this is the reset vector. If you set up the first 8 bytes correctly, the machine would start, okay? And then whatever you put in the reset handle, it would execute, okay? So this is exactly what I need. I don't want any interrupts, okay? I don't want any heap. I don't want any multitasker. It has this thing. I think in the software it emphasizes that you can do preemptive multitasking switching. Okay, so very powerful. But then the software just got so complicated. And since I don't need any of these things, all I need is this reset vector, and the machine will start. Okay. And so what in fourth, all I need is an UART. So I just need to have the UART working, and then I can put fourth on. So I found a hello world tutorial, and that just shows me the code then that you need to send out the hello world to the serial port. So that was a very nice tutorial, and I implemented the tutorial and another tutorial which is turning the LEDs on and off. So with these 3 tutorials, I was able to get myself give me enough confidence that I can put in my code into this and started doing the 4th. So I was very proud. I'm very proud of this minimum boot code, and I think that yes, there's complexity, and there's lots of complexity in this board, but irreducible complexity. What's the minimum set to get it to work? So I think software-wise, there's 8 bytes. That's the key. Okay, just understand that 8 bytes, and you're on your way to a good start. So I need only 1 UART. Of the 6 UART, of course, I just picked the USR number 1. But the UART, it has 9 GPIO ports, and all the various devices are borrowing pins from the from the GPIO ports. So most of the GPIO pins are multifunctional. So you can set up the GPIO for input, for output, and for analog function, and for alternative function. Okay, that's when you assign that particular pin for particular for other devices other than the GPIO. So you have to initialize them properly. So select the proper pins, and for that, at each particular pin, select the proper alternative functions, and then you can set up things to work the way you want it. So for USR1, it has transmit and receive pin. But transmit and receive pin, they have 2 different assignments. So you can actually assign it to the 2 different assignments. One is the GPIO A 9 and 10 for the transmitter and the receiver. And another assignment is GPIO B for the B6 and B7 for transmit and RF. So depend upon how you want to set up on your board, you can make the selection and make the proper initialization. On this discovery board, there's 4 LEDs in the center, and they are connected to GPIO B. So I thought, well, it's always nice to get these LEDs to line up when you execute 4th. Okay, just make sure that you demonstrate that you are in control. But so I need 3 devices. But all the devices has to be clocked. Okay. And the design is very nice in that if you don't clock the device is not active and doesn't draw any power. But if you want to use any of them, you have to provide clocks. Okay, and the clock is controlled by this device called the reset clock control. So in this register, you just tell it which I/O device needs the clock, and it would route the clock up properly. So to get the the discovery to run eForth, I have to initialize these 4 ports, and then it's not a big deal, you know. Just read these 4 chapters, and of course the chapter on the flash memory to do the virtual memory switching. So that was the if I initialize these 4 ports properly and demonstrate I can send a hello world to the output, then basically eForth has you have all the I/O capability that's needed in eForth. But on this board, on many other boards, the USB has the communication port in it, like the Arduino. Arduino has the download facility and also the communication facility. So it actually are 2 devices in Arduino. So here it does not have the communication capability. So I have to use the I/O ports to the which is hooked up to the USR1. So I first on the 4th Arduino board, it used the GPIO-A port for the transmitter and receiver. So naturally, I use also the USR1 using the GPIO-A for output. But tried a long time, spent a long time trying to get the port A to work. But they just wouldn't work. I have to switch to the alternative B port, PB6 and PB7, for the transmitter and receiver to work. And then I found out that the same line for the GPIO-A was used by this micro USB. So they're using the same line, but I don't understand it. I'm not using that port. I'm not using that chip. That chip is not initialized anyway. But it just would not allow me to send out the characters correctly. But switching to port B, that works fine. That works all right. And then I need to do a terminal. Then I need RS-32 to USB converter. And then I just I got lots of Arduino there, and so I use one Arduino. The Arduino, the USB has the download. It has 2 devices in the USB: a download device and also a USB serial port. So it has a serial port there. If I remove the CPU from the Arduino board, then I can just use the transmit and receive pins for the eForth to talker terminal. And here I have the let me see. So here I can switch over. I think I need to turn this guy on. Okay. Why it didn't so well? Okay. So this is 4th. Okay. And this is the 4th on the discovery board, hooked up to the Arduino as a terminal device. Okay. And right now, this discovery board is not connected to the ST-Link. So it's running pretty much standalone and just sending out the signal to the hyperterminal on the other computer. And for the fourth Uno board, and the UART is implemented on the on its USB port. So I have the UART there, and it is using the UART for downloading purposes. It can download the binary hex files into this port. So here, let me see. Here, this USB port is connected direct to this computer, and then this computer has the serial port there. Okay, notice that this one is 7.30, and the other one, if you have noticed, is 720. So there's two different versions of eForce implemented on two different ports. Let me see. So here, okay. So here, this fourth. I've reworked the eForce quite a bit in this port. Okay, so I have only 174 commands remain, but 23 of the system commands I have the headers comment out. So these commands you rarely use it when you are typing, when you are programming. So there's no need of them in the there's no need to keep their heads in the dictionary. So it also made the list much shorter and looked pretty nice. So the last code I put in is turnkey. So here we have the system running in RAM, and you can compile, you can define, download all the different applications into the system, and then after your application is fully debugged, you want to save it back into the flash. So this is you load application, you load application, you load application, and finally you are happy with it. The first thing you need to do is erase the sectors. Okay, the STM32F4 the flash memory is organized in sectors, and the first 4 sectors are 16 KB each. And that's what I'm using. Okay, in my phone, I'm only using, although I can use up to 128 kilobytes, I only use 64. So that if you erase the first 4 sectors, that's 64 kilobytes. If your code is less than 16 kilobytes, then 0 erase sector, erase the first sector, and that's all you need. And then you take your application and store in boot, and you execute turnkey. And the turnkey would copy all the user variables back to the table in the dictionary, and then copy the entire dictionary back into Flash. And that way, if you do reset or turn the power up, APPL, this thing would get executed on Buddha. So I think this is a very, very nice setup that you can do what I call the firmware engineering. Okay, write your code and test them on real computer, and then save everything for a turnkey system. So I think I'll just make a few comments on the discovery. So it has 14 counter timers. Yeah, in the Arduino, I was struggling to get the some counter timers to run my speakers. It has 3 counter timers, and as I can demonstrate a couple years ago, I was playing box music and only select the 3-part pieces. And now 14 counter timers and 80 digital I/O pins. You can run a piano keyboard.
This wasn't a MIDI, I think, was it?
Beg your pardon?
Was it MIDI or is it just your own?
It's not MIDI. It's the running speakers.
Okay.
Using square waves to drive the speakers, simulate pipes. Yeah.
Okay.
So it's you know, in the 80s, I got when we were working on the IBM PC, the Taiwanese Taiwan FIG gave me some boards, I/O card, and which has 4 8255 and 4 8256. The 8256 got one chip got 3 counter timers. They got 4, so I got 12 channels, and they got 4 8255, and each of them has 24 I/O pins, right? So 4 of them, you get 96 pins. I was using that to implement a regular keyboard and a 12-channel electronic organ. And I almost got the whole thing here, and plus the chip, plus the CPU for free. Okay. And it has a 3 12-bit 2.4 megahertz A to D converters.
Mega samples per second.
Yes, 2.4 mega samples per second for 1 channel. Okay, and for 3, it can run 3 channels concurrently. So the total throughput, the maximum throughput, is 7.2 meg samples per second. Wow, that's a very nice. And then 24 channels. Okay, it doesn't have an LCD on it, but it has an LCD parallel interfacing on it. So if you do have an LCD display, well, you can actually. It looks like a digital storage oscilloscope to me. Okay.
Yeah.
And the
Slow one, perhaps.
yeah, well, 2.4 megahertz. That's pretty good. You know, most of the things you can. If you do you need anything higher.
That's like a 500 kilohertz scope.
Yeah.
Almost.
Yeah. Well, I think it's 1 megahertz for sure. And
if you've got a signal that can get by with 2.4 samples,
yeah.
Nyquist says it's not going to look. It's going to be ugly.
Okay. So this board is nice that it has this SWD debug port. So you can forget about this. You don't need that. You can hook up to another board and debug another board. So this is very nice. usually it costs money. I think the U-Link, usually the U-Link, that's a little card, a little box, debug box, costs $150 or something. But now it's free. So, okay, I talked about this connection. Okay, this is my setup. Yeah, this is what I have on board. Okay, here is my serial port, USB to serial converter in an Arduino board without a CPU. And this is my Discovery, doing everything. And then this is the fourth Arduino with the SWD connection. And then it has its own serial port to the for E4. So I was spending 3 weeks writing this manual, and I'm pretty happy with it. I think you've all seen it, but they were kind of organized, not organized very nicely. Now I have them all really organized, very pretty. So I talk about the chip, talk about how to assemble the E4, and then the source code. This source code is basically a code walkthrough. Okay, I'm just trying to read the code from the first line to the last, and then I have divide them nicely into a virtual force machine, E4 kernel, text interpreter, force compiler, and debugging tools. Yeah. Okay, I think the demo you have, I have already done the demo. So the first thing is the Discovery talking to the terminal through the Arduino board. And this is the fourth Arduino. Another picture, I think. Let me see. This side is the output, and these are the switching transistors for output. And on top, these are the input, optical isolated inputs. And then here is the chip, and the USB is over on top. It has another USB on here. I don't know what to do with it. Okay. And the chip has a USB support, and I haven't really looked into it yet. So yeah.
It could. I bet it does have OTG support.
Mm-hmm.
So that you can run both devices. You put devices and you can put up your PC if you want.
Yeah. Mm-hmm. Right. Huge library. Okay.
Oh, yeah.
Yeah, I think it has all the sort. Well, if you care to, the library is there. If you care to read it, and if you know how to use the library, the functions are there. Okay. Okay, and this is everything together. The Brotherhood. So. Okay, I think the Discovery is the cheapest ARM microcontroller board ever. Actually, one comment I made was that it's not an ARM chip anymore. Okay, the three STM32F4 is not an ARM chip. It's a thumb chip. Okay.
Oh,
yeah.
yes.
So you look inside, there's no arm. There's only one thumb left. Okay. Very interesting. Another comment I made was that the ARM Holdings, the parent company, which released the ARM, if you look through the documentation, they have already ceased to use ARM as the name of the chips. And this chip is a Cortex M4, okay? Not an ARM chip, but Cortex M4 chip. And if you look inside the instruction set, there's no ARM, it's not ARM instruction set, it's not thumb instruction set, it's a thumb 2 instruction set, okay? So that's a difference. And the first shock I had with using the system was that, you know, the original code that I wrote for the ECML chip has the directive, the ARM directive. So it specifies you assemble everything 32-bit, and if you use the thumb directive, it will assemble into 16-bit instructions. So when I try to assemble that file, hundreds of error messages, just pages and pages of error messages. I couldn't figure out what was happening.
And there are some C programmers who weren't bothered by that.
No, they don't bother.
Oh, just ignore it.
Yeah, because now I look at the startup code provided with the system, and first thing I notice is thumb. You know, I said, why thumb? I want ARM. I don't want thumb. But if you put the thumb directive, it's much happier. Okay, and then it's you start from there. But apparently it just phase out the ARM. Okay, all you need to do is a thumb. But then it's not thumb is not phased out altogether, and there's lots of tails left in it, and which is which bothers me. One thing is that if you in all the thumb instructions, if you jump to a target address, the address has to be the least significant bit B0 has to be set. Okay, so the address is all odd. It has to be odd. Why? Because this last bit is not used as an address bit. It's a bit which sets the thumb state. Okay, it's in the status register. There is one bit called a T, and if you are executing a thumb instruction, a T bit must be set. If the T bit is cleared, it's assuming the instruction is it's a 32-bit ARM instruction. But since all the instructions are thumb instruction, why do you need that bit? And you know the system just keep on crash. Okay, it's I have aligned everything nicely to the 32-bit word boundaries, and that the assembler was not happy with that either. Okay, it tries to align things in 16-bit boundaries, and whenever I have a 32-bit, it says no. It's I got everything 32-bit, assuming all the instructions are 32-bit, but the thumb would assemble 16-bit instructions, and then it is warn me that, well, there's a hole there. So the assemblers are inserting 2 more bytes. Why do I need that 2 more bytes? But if you don't have the 2 more bytes, well, it doesn't work. You know, the things would crash. And then if the jump, most of the instruction, if the assembler would generate the jump and the branch with the odd address. But when I'm using, you know, in Forth, when I do a question branch, do a branch or do a next loop, I have to give the address to jump to, and that address has to be up. Or yeah. But I think later I found that, well, it's not not a big deal. When I do a jump, when I do a branch, when I do a next, well, I just set the least significant bit and then jump. Most of the time it worked, but then the fetch execute wasn't working. When I do the turnkey, so I store address into the tick boot and let the fetch execute to execute that vector the instruction. It always crashes. and then found I have to put an odd address in it for it to jump correctly. So that was I did it, and after a couple of days, I said, well, you know, actually that's an E4 bug. Okay, it's not their fault; it's my fault. I should have I should have known that, and I should have made provision for that. So in the fetch execute, that was one instruction I didn't set the least significant bit of the address. So I set the bit, and then it works for nicely. So these are some of the things, many of the problems I encountered. And I think this is the first microcontroller I didn't feel constrained. Okay, when I do fourth, you know, usually it's not enough RAM. Yeah, I can use flash, but then, you know, to write into flash, that's a lot of hassle. So it's always when you are writing forth for these chips with limited resources, especially limited RAM. You always feel, I wish I had more RAM, and this is my wish came true. And the peripherals are just overwhelmed. Okay, there's so many of them that. But it will be interesting if you really need them. It's there. I was looking at the accelerometer. So, and then I look at the schematics and read the documentation carefully. And the accelerometer is hooked onto the SPI as an SPI device. So it is hooked onto an SPI port. And then I have to read the SPI, and I have to read the accelerometer. I haven't finished reading yet, but it would be nice to replicate the accelerometer demo in forth. And you know, we saw so much memory, so much I/O. Wow, it's a wow chip. Okay, and if you think of any substantial application, this is the one that you should consider. Even with the ugly thumb2 instruction set, but the nice thing about forth is that it's a forth virtual machine, and you don't have to deal with all this oddity in it. But it has some other things is that it has the floating point. It doesn't have the Intel style floating point coprocessor, but it has floating. It can handle floating point, and it has lots of multiplication, multiply, accumulate instruction. And so these are very nice things if you do the DSP work. Questions?
Cool.
Yeah. Yeah.
Can you give us some idea? You said that there were a number of headers that aren't even they're all commented out.
Yes.
Any idea what they do, or?
Oh,
they're called?
yeah. It's
What sort of stuff they chose to comment out?
Yeah. It's the for example, query branch. Okay. Have you ever used query branch?
What was that again?
Query branch. Yeah.
Question mark print. Oh.
Yeah. Yeah. You use if else then, right?
Yeah.
Yeah. So the query branch is never used by an end user.
Okay.
Okay. It's compiled by if. Okay.
I see.
Yeah. So these things are very low level thing, and in the original eForce model, everything has header, so you can if you care, you can actually execute the query branch.
It's only a header, so that it's compiled.
Yes. So I just removed the header.
Yes.
So the function is still there. Okay. So it's there.
The address.
Yeah, right.
You don't really need the header.
Yeah. But
Once you're done compiling.
yeah. But I think.
You don't need the header.
Mm-hmm.
If you're meta compiling,
Yeah, if you are
you need this for if to work, for if then to work, then it needs a header, so that the meta compiler can find it, stick it in, and then the header can go away.
Yeah. If you use meta compiler, okay. If you don't use meta compiler, as here, I'm just use straight assembly. You don't need the header. If you don't use it, then you can remove it. Yeah, right. Yeah. So you know, 23 commands of this kind. These are deep, buried deep in the kernel that the user never sees. But I think sometimes I may have to put them back, because I have the decompiler. I have decompiler in it. Okay. Yeah, there you need it. Yeah, there you need that. But if you don't mind looking at that query branch as the data, it's okay. Yeah.
For this sort of thing.
Yeah, right. Yeah.
Okay, look at the head first.
You can get Android for a bunch of sources. Android is on many sources.
Yeah, it's nice. You know,
You guys remember a couple of years back when there was an attempt made to make an open source cell phone? I actually know at least one guy that bought it and was hacking it. It was his everyday phone.
Yeah, you know.
Talk about an optimist.
Yeah, it's not the cell phone is much sophisticated this, right? The problem is that the Game Boy is that you have only this many keys. That's a problem. Yeah.
And that's why the screen has gotten bigger phones, so that they can put the keypad on the screen, and you can take larger pictures.
Yeah.
Remember when your PVA
had
a little stylus that would come out, so you could actually touch little tiny points? I've seen oscilloscopes now that need the stylus. It's the mini tablets. Yeah. The crossover between tablet and phone. Remember PDAs? Oh yes.
Well, you know the iPad. You know, just think iPad. Yeah. Now you get a big screen big enough that you can have the keyboard.
The problem with the iPad
and it's the input.
It's not. You can get tablet have the SM radio in there. Yeah, but that's just the data radio. You can't use it as a phone. You can buy a big phone. The Galaxy, big screen Galaxy is sort of almost a tablet.
They have a crossover that has the full
Mhm.
capability.
Right.
Mhm.
But they-
Well, you don't hold it up to your ear. You have a Bluetooth headset.
No, actually, people do. I've seen people hold up to their head.
The 5-inch tablets, you can do that.
Uh-huh.
Yeah, there's a cartoonist that's mocking the guy's carrying his phone in the backpack.
Yeah, I think I'm thinking of doing a project. Just use the regular, phone, and do put that cell phone in it, and then you can have it and dial and ring and talk.
And those on the rotary phone that are either USB or actually Bluetooth. You have a full handset.
Uh-huh. Yeah, well, I think I'm just carry this phone around and set it down there and we can call. Yeah. That would be very impressive.
Those would be the Chinese
Yeah. Yeah, I think you carry this phone around, sit on the table, and rings, and you talk, you put it back, and you dial.
That might be a nice Bluetooth
Yeah.
device to have.
Uh-huh.
That you go to your office and have the phone sitting there next to your cell phone. Don't have to ring.
So Tim, you might be able to get your son interested in this.
No. I might get my grandson to interested in it.
That's the higher hope.
Yes.
Our children, no, don't do it.
Yeah, but
They have to skip generations, I understand.
yeah. My grandson, his dad is internal medicine doctor. My daughter is the optometrist. And so, well, we used to ask him, well, what do you want to do in the future? And he said, oh, I want a policeman. I want to be a doctor. And lately, I think last time we asked him, he said, well, I want to be a scientist. And maybe I want to be an electric engineer, electronic technician. Okay.
Yeah.
That was after I showed him the Christmas tree and the cube. Oh, he was thinking. So there's hope. There's hope. Last time he was in my house, I showed him the cube, and I said, "Oh, I can tell you how to program it. Just come in." And so I hook it up, and I hit the key, and it says okay, and I say, okay, type in this, a number 1010 drive. And he saw one light. Oh, he's having lots of fun playing with it. We put in, well, I told him he didn't know anything about the hacks. I just tell him, when you type a number 0 to 9 and A to F. Okay, that's all the number you are. Oh, he was able to type and say drive. Okay, thank you very much. I think it's time to lunch. All right.
Yeah, it's lunchtime.
Do you want to make an announcement?
Yep. Shut down for a while. Well, as you probably heard, we're going to be heading out to lunch. So we're going to kill this transmission, and we'll be back in about an hour-ish. And we'll send out the links again for the second part. See you then.
Why couldn't you join us for lunch?
Yeah, I could do that, but yeah.